Here we go. Letter E. Pretty similar to the one that came right before this with the sine squared. I'm thinking we're going to be factoring this one again. Now this, I believe, turns out to be a perfect square trinomial. Again, I'm thinking 4x squared minus 4x plus 1. How does that factor? Not mistaken, I think it's 2x minus 1 squared equals 0. Right? So that would be 4x squared minus 4x plus 1. So if that's the case, then we're going to factor the one above it in a similar fashion. That is, parentheses, 2 times the cosine of x minus 1 in place of x, cosine of x squared, equals 0. Now, we could do the square root property. Pretty convenient because you're just going to get plus or minus 0, or set each factor equal to 0, which is identical factors. So bottom line is you get 2 cosine of x minus 1 equals 0. You add 1, divide by 2, cosine of x equals 1/2. Now from that, we go to the principal value. Principal value is going to be cosine inverse of 1/2. Which hopefully we know by now is 60 degrees, or your pi thirds, I suppose we can write that. We'll write it when we write our solutions. So we go from 0 to 360. So 0 to 360. We would say, is 60 a solution? And of course the answer is yes. So 60 is one solution in degrees. We go 0 to 2 pi. We would say 60 is pi thirds. Now, next question is, where else is cosine, maybe I should be pointing to this, where else is cosine positive besides quadrant 1, which we already have for our principal value? The answer is quadrant 4. So we need to go to a quadrant 4 angle with a reference of 60. And then just ask ourselves what that angle is. That is 300 degrees, which is the other solution in degrees. As far as radians are concerned, that would be 5 pi thirds. And there we have it, from 0 to 360, 0 to 2 pi. As far as fancy methods, not seeing it. So we go to all values. Again, the all values a lot of times just mechanicals. Here we go. So what do we got? We got ourselves a 60, and all angles coterminal with a 60. Plus 360k, we got 300, plus all angles coterminal with 300. Or as far as radians are concerned, we can say pi thirds plus all angles coterminal, or 5 pi thirds plus all angles coterminal. Kind of on the downswing once you get past these. This pretty much, there's rare times we can actually kind of condense these, but it doesn't happen very often. All right, letter F. Let's change colors here. Hopefully that's suitable. All right, looks like we got some options here. We got a cosine 2 theta, and this is already a cosine. I'm thinking I'm going to need a substitution for sine squared. Yeah, probably. And I'm going to pick the 2 cosine squared theta minus 1, just to agree with that cosine. So I'm going to call this 1 minus cosine squared. So substitute sine squared theta as 1 minus cosine squared, cosine 2 theta as 2 cosine squared theta minus 1 from the double angle identity, just to accommodate the cosine of theta. I think that's what we're going to have to do. All right, so without rewriting all this again, I can start combining some terms here. I think I would lead off my problem with the 2 cosine squared theta, this thing. So let's cross that off. Know it's been used. 1 minus 1, well, those are just going to cancel outright, which is nice. minus cosine squared theta. I didn't even notice that, so I should have combined it. Minus cosine theta, and I don't think I really saved any time by doing that because I still have to combine these two cosine squareds into one cosine squared. So 1 cosine squared theta minus a cosine of theta equals 0. Factor your GCF now. So cosine theta times cosine theta minus 1. So two things. Cosine theta could be 0, or cosine theta minus 1 could be 0. This one, we'll just say cosine of theta equals 1. All right, we've been through enough of these quadrantals. Draw your cosine graph real quick, just for reference sake. I think it helps. Again, I know it helps. It's easier to see what these quadrantals are. So cosine, let's get a quick sketch, and you'll see what these quadrantals need to be. All right, where is cosine of theta equals 0 from 0 to 2 pi? Well, it's 0 here at pi halves, and it's 0 here at 3 pi halves. So let's just start going with it's 0 at pi halves, which is 90, I'll get it, and 3 pi halves, which is 270. Right, as far as radians are concerned, we're looking at pi halves. We're looking at 3 pi halves. Okay, over here, where is cosine of theta equal to 1 from 0 to 2 pi? Well, 0 is inclusive there, meaning, we got a bracket on the 0, so we do include that one. 0 radians, and where else is it 1? Well, at 2 pi radians. However, 2 pi is just out of our restriction area, though. So we don't take the 2 pi. We're just going to have to go with 0 radians, which is 0 degrees, and 0 radians. Right. As far as all values are concerned for this one, 90 to 70, that one actually we can condense. I mean, if you just put 90 plus 360k and 270 plus 360k, that's fine. But you're seeing that each solution, well, it's, again, I say diametrically opposed. So you got 90, and then it goes another 180 degrees. Your next solution will be 180 degrees away from that one. The next one, 180 degrees away from that one. So we can just take the smaller of the two if we want to condense this and say, okay, for all values, we could just say it's 90 plus every multiple of 180. And again, that k is an integer, so this is positive or negative. We could go positive or negative. And that would actually incorporate every coterminal with 270 as well. So 90, 180 away is the next solution, 180 away is the next solution, and that works as well. All right, now as far as the 0 degrees, I'm not seeing anything we can do with just 1, so 0 plus 360k, and you'll see in the back that I don't write the 0 plus because we never write 0 plus anything. We just say 360k. So that covers all values for the degrees. I should be putting degrees there. As far as radians are concerned, we can do the same thing. That is pi halves plus 180 would be pi. Okay, every multiple of pi, as well as 2 pi. Okay, again, not 0 plus, just 2 pi k. It's not that big of a deal, but we don't tend to write 0 plus. All right, moving right along.